Hello there, Mr. Sutton here, bringing you this Pre-Cal Honors 3-4 lesson on complex fractions. In this one, we will be learning what these are and how to simplify complex fractions. For the warm-up on this one, we have this little monstrosity to look at here. This is an example of what we would call a complex fraction. Specifically, this means that we have fractions within a fraction. Might be just one fraction, might be multiple fractions, but we've got fractions within fractions. So pause the video and using whatever method you feel appropriate, see how far you can get on simplifying this one. And by simplified, we mean we want just one fraction without fractions inside of it. All right, let's see how this worked out. Now, there's actually two different strategies for dealing with this, at least two strategies. First strategy would be just to go with what we know, and really all we know at this point is how to simplify fractions like the one in the denominator here. Like we could add 1/2 and 7/8 together. So strategy one is to simplify the numerator and denominator as much as we can using the fraction rules that we've already got. So in this denominator, for example, to add these, we know that we need a least common denominator, an LCD. The LCD of 2 and 8, that's going to be the smallest number that these both go into, and that would actually be 8. So in order to add these together, I need them to both have 8s in my denominators. This 1/2, I can express this as 4/8 if I multiply it by 4/4. And 3/4 can't really do too much up there, but we can add 4/8 and 7/8. So adding our numerators down here, this is going to give us 11/8 in the denominator of the main fraction. And at this point, we've really just got division here. This is just really division in another form. So our last step is just going to be to divide this as we normally would. We'll treat this as 3/4 divided by 11/8. And just a little review, when you're dividing fractions, you're going to multiply by the reciprocal, or same change flip. So this is actually equal to 3/4 times, and then we have to flip this bottom one here, 8/11. Now we notice here that the 8 and the 4 can reduce. This can reduce to a 2/1. And now if I multiply straight across, I end up with 3 times 2, or 6, and 1 times 11 giving me 11, so 6/11. We're going to take another look at this problem now because there's another way to approach this. So that last approach wasn't bad. I mean, it relies on what we already know. The trouble is, if I'm doing something other than using a complex fraction with constants in it, if I have like x's and other kinds of variables, that could get very messy very quickly. Adding polynomial rational expressions together, not a lot of fun. So another way to do this type of problem that doesn't rely on all of that stuff is as follows. So here's strategy 2. First part of this strategy is we're going to find an LCD, not just for kind of like the subfractions here within one side. We're going to find the LCD for all the subfractions in this entire complex fraction. So we're looking for the LCD for 4, 2, and 8. Take a moment to figure out what that is. All right, so hopefully you came up with 8. That's the smallest number that 8, 4, and 2 all go into. And if you're having trouble getting LCDs, I would just take like the biggest number and just take multiples of that until you find something that's divisible by the other numbers. So we have this LCD of 8. What do we do with it? So this is going to be a little bit different than what you're used to. But what we're going to do with it is we are going to multiply this main fraction by the LCD over itself, which essentially means that we're multiplying each subfraction in this entire thing by the LCD over 1. So visually, here's what that looks like. I'm going to have 8/1 over 8/1 that I'm multiplying by. Now, first off, this is legal because if you divide all this out, you've really got 8 divided by 8, which is just 1. So we're really just multiplying by 1, and that doesn't change the value. So we're good on that score. Now, the reason that this is actually very helpful is if I have an 8 in all the numerators of these subfractions, that means I'm going to have something that can cancel out all the denominators of all these subfractions. So if you don't really believe me, just let's watch the magic happen here. So my next step is going to be to simplify all this and reduce it. So here's what that means. I'm going to have an 8 times 3 over 4 in the top of my main fraction. Down below, this is going to be an 8 times 1/2 and an 8 times 7 over 8. And this little 1 down here, we're just not going to worry about that because that gets multiplied away. All right, so going through here now, we have 8 divided by 4. We can reduce that. That's going to give me a 2 over an invisible 1 that I'm not going to bother writing anymore. And if I clean up what's left over here, 2 times 3 gives me just a 6 on top of this whole main fraction. Now down here, the 8 and the 2 are going to reduce. That's going to give me a 4 times 1, which is just 4. And finally, these 8s here cancel out completely, leaving me with just a plus 7. So the reason, again, that we chose the LCD is this has all the factors we need to cancel out all the denominators. And that's just what we did there. So now just taking this the rest of the way, 4 plus 7 is 11, so we end up with, again, 6 over 11. So just another way of doing it. It probably takes about the same amount of time if you're just doing normal numbers, but once you start throwing x's in there, I think this process tends to be a little bit faster. At this point, we're going to introduce some problems that have variables in them. So you're going to pause the video in just a moment and try this out with whichever method you like best. Just full disclosure, I'm going to use the second method with the LCD for all the subfractions, just because that's newer than anything else that we've done before. So I'm going to give you a few more examples of that. But if you like the other method, feel free to use that too. All right, so going through here, first I'm going to find the LCD again for all of the subfractions. So let me take a look at my numbers first. I've got 3 and 4 in those subdenominators. So the LCD for 3 and 4, that's going to be 12. That's the smallest thing that 3 and 4 both go into. Another way you could think about it is what would you need to cancel out the 3 and the 4? And 12 is the only number that does for both of those. Now also in our LCD, we have to have an x because of this x right here. So we'll have an x in there as well. So now that I have an LCD that could cancel out each of the denominators, again, I'm going to go through and multiply the top and the bottom of my main fraction by 12x. So we have 12x over 1 times 12x over 1. So effectively then we have a 12x times the x squared up there. We have a 12x times this 12, and a 12x times this x right here. And again, notice I'm only putting that in the numerator of all these subfractions. Okay, going through now and reducing. Here in the top we have 12 over 3, which reduces to 4. And then we have an x and an x squared up there as well. So 4x times x squared gives us 4x cubed. And that's all that's left up there. Down below we have these x's canceling out completely, leaving me with 12 times 12 for 144. And the 12 and the 4 reduced to 3 over 1, giving me 3x times x, which is 3x squared. And I'm adding that. Now, at this point in the problem, especially since we have variables involved, you might want to factor and see if you can reduce this a little bit more. It turns out that we can actually factor the denominator by taking out a 3, but it's not really going to help us because that 3 is not going to cancel out with anything in the numerator. So that's as good as this one is going to get. We'll do one more example, pause the video, and give this one a shot. All right, so for this one, I could see the argument in just simplifying the denominator and then doing a little same change flip, because in the denominator here, these subdenominators are the same, so we could very quickly combine this into 2x minus 2 over x minus 3, and then multiply by x minus 3 over 2x minus 2, and finish this problem off fairly quickly. But again, I'm going to show you that other technique just so you can see it. So here, the LCD, we're going to need an x for this x up here, and we're also going to need an x minus 3 for these x minus 3s down here. Multiplying through by x times x minus 3 over itself, we end up with x minus 3 times the 2 up there, and also times the 2x down here, and also times this 2. So it's a kind of clunky in the beginning, a lot of writing. I do recommend you write it out each time so that it's easier for you to see what's being canceled out and what's being left behind when you do that next step. So that next step then, we've got these x's up here canceling out. That leaves me with 2 and times the x minus 3. I'll go ahead and distribute that out because I don't know what I'm going to be doing later on. So we've got 2x minus 6. And then down here, these x minus 3's in this first fraction cancel. X times 2x gives me 2x squared. And these x minus 3's are canceling. So this is going to be a minus, don't lose the minus there, minus x times 2 or 2x. At this point, I'm going to go ahead and factor this to see if I can reduce my fraction at all. So in the numerator, I can take a 2 out of these, leaving me with an x minus 3. Denominator, I can actually do a little bit better and take out a 2 and an x, leaving me with an x minus 1. And if I look at my factors, I see that I have some 2's that I can cancel out. Not anything else that I can do here. So in my numerator then, final answer, I've got an x minus 3 all over x parentheses, x minus 1, or you could distribute that to be x squared minus x. Doesn't really matter at this point. So that's going to be it for this one. Hopefully you didn't find this process too complex. Till next time, this is Mr. Sutton signing off.